Hello everyone. Today I'm excited to present ARIA, our novel approach of optimizing vision foundation model inference on mobile devices to enable immersive augmented reality experiences. I am Chanyoung Jung, and this work is done with our amazing colleagues from Yonsei University and Uppsala University. Mobile augmented reality is expanding into areas like gaming or tactical applications, demanding real-time scene understanding from its camera stream. To achieve this, we believe that on-device processing is essential, as relying on the cloud may introduce unacceptable delays or privacy issues. These latency-critical applications highlight the need for efficient real-time vision processing directly on mobile devices. For AR to work seamlessly, devices must not just capture images, but also understand the environment in real time. Two key pieces of information are depth and semantics, knowing how far objects are and what surfaces they represent. Accurate depth enables correct 3D placement, while semantics guide realistic interaction. To deliver this, frameworks like AR Core use deep neural networks that provide pixel-level predictions, demanding efficient and real-time processing. AR applications must work across highly diverse user environments. However, traditional domain-specific models like CNNs often fail to generalize beyond the domains they were trained on, leading to errors like incorrect depth estimation. In contrast, vision foundation models, such as VFMs, which are based on vision transformer architecture and pre-trained on large, diverse datasets, offer much stronger generalization. This makes VFMs a promising option for delivering reliable AR experiences across varied real-world scenarios. Here, we compare CNNs with VFMs on real-world tasks like depth estimation and semantic segmentation. VFMs not only provide much clearer, but also achieve almost 3 times higher accuracy in zero-shot prediction, demonstrating strong generalization across diverse environments. However, running VFM on mobile devices introduces significant challenges due to their heavy computational demands. VFM requires high computational fidelity to generalize well across diverse environments. Specifically, it needs high input resolution and high arithmetic precision like FP32 or FP16 to maintain prediction quality. As shown in the graph, increasing resolution consistently reduces the error of depth estimation, improving accuracy and capturing much finer details. Besides resolution, precision is also critical to maintain accuracy. When we move from FP16 to int8, we see a 3.6 times drop in depth estimation accuracy. The visual results show that int8 inference introduces severe errors, distorting the depth map. This demonstrates that floating point operations are necessary to preserve the high accuracy of VFM. While high fidelity is crucial, it comes with significant latency costs on mobile. As resolution increases, latency rises sharply for both GPUs and NPUs, especially with floating point precision. On the NPU side, NPU FP16 can offer real-time inference at low resolutions, but suffers from low accuracy due to low-resolution artifacts, as we previously observed, and shows drastically increased latency at higher resolutions. To better understand this latency problem, we break down a single vision transformer layer by its operation type. As resolution increases, matrix multiplication and softmax operations, which are key components of attention in VFM, dominate the latency due to its O(n)² computational complexity and limited parallelism of NPU. While GPU can alleviate the drastic increasement of latency by its strong parallelism compared to NPU, it also cannot satisfy the demands of accuracy and real-time requirement of AR. So, as we've seen, neither the GPU nor the NPU can alone meet both accuracy and real-time requirements for VFM inference. So this leads us to our key insight. We need to utilize both GPU and NPU in a smart and complementary way. Specifically, NPUs are highly effective, even achieving real-time for low-resolution images, which can be considered as small data, while GPUs are more efficient for large, high-resolution data. By combining their strengths, we can overcome the limitations of single-processor approaches. To this end, we propose ARIA, the first mobile system that efficiently deploys vision foundation models by intelligently utilizing heterogeneous mobile processors. The key idea behind ARIA is to leverage the heterogeneity of mobile processors through parallel and selective inference. ARIA runs full-frame, high-fidelity predictions periodically on the GPU to achieve high accuracy, while the NPU concurrently performs fast, lightweight updates on only the dynamic regions of the scene to meet the latency requirement of mobile AR. Although the key idea of ARIA sounds simple, realizing it efficiently on mobile poses several challenges. The first challenge is how to accurately find dynamic regions. Pixel-level methods like optical flow can detect fine-grained changes, but they are too slow for mobile devices. Block-level approaches are faster, but often include static areas, wasting computation. So we need a solution that is both precise and lightweight to find dynamic regions. This is crucial to ensure that NPU updates only the necessary parts of the frame to meet the latency requirement. The second challenge is how to properly merge the GPU and NPU results. The GPU output can become outdated due to periodic updates, and the NPU's partial updates underutilize VFM's global context. As shown in here, the naive merging leads to visual inconsistencies like artifacts. Therefore, proper alignment and blending are crucial to maintain accuracy across frames. The last challenge is how to schedule the system under dynamic conditions. Mobile GPUs suffer from thermal throttling, slowing down as the device heats up. At the same time, camera motion affects how quickly the scene changes, requiring faster updates. A static scheduling policy cannot handle these runtime variations. Therefore, we need a dynamic scheduler that adapts GPU and NPU workloads based on current device and scene conditions. Now, let's move on to ARIA's core techniques that address these challenges by first looking at the basic workflow of Vision Foundation model. VFM processes images by first splitting them into patches, which are the basic units handled by the Vision Transformer encoder. The encoder generates patch embedding features, which are then decoded to produce final predictions like depths or segmentation maps. ARIA builds upon this structure to efficiently find dynamic regions without much overhead. Let me explain how ARIA finds dynamic regions step by step to address the first challenge. First, we extract patch embeddings from the current GPU full-frame inference. Next, we estimate camera motion between frames using pose data from the device. With this motion information, we generate a patch flow and warp previous patch embeddings to align them with the current frame. I will explain patch flow at next slide. Then, we calculate cosine similarity between the warped and the embeddings. Here, patches with low similarity indicate dynamic changes and are identified as dynamic candidates. And finally, these patches are grouped into dynamic regions. After dynamic region identification, ARIA continuously tracks these regions across frames using the previous motion information for each regions. This avoids computation, ensuring accurate and efficient tracking of dynamic regions over time. Next, to handle the misalignment between GPU and NPU predictions, ARIA introduces a dynamics-aware spatial-temporal alignment technique. Let's first look at the temporal alignment for GPU predictions. The whole point of this technique is to warp previous embedding features from GPU properly by using the motion information. First, we input camera motion into an MLP to generate a motion embedding. This motion embedding is concatenated with full-frame patch embedding features from the GPU inference to form a latent embedding. Another MLP takes this latent embedding and predicts the patch flow, representing how each patch moves between frames. And finally, using the predicted patch flow, we warp the full-frame features to align them with the current frame. This ensures the full-frame predictions stay temporally consistent, even without running a full GPU inference every frame. After temporal alignment, ARIA also ensures the spatial consistency of NPU predictions. First, we apply adaptive padding around the detected dynamic regions based on their motion vectors. This extra context helps avoid boundary artifacts during merging and alleviates inconsistencies by larger receptive fields. We then mask these regions with the temporally aligned GPU features to prepare for finer fusion. In parallel, these padded dynamic regions are passed through a lightweight VFM encoder on the NPU, and this generates the spatially aligned NPU predictions. Finally, the GPU and NPU predictions are fused together via the VFM decoder to produce the finer, visually consistent output. This spatio-temporal alignment ensures that ARIA maintains high visual quality and stable predictions of heterogeneous processing. Finally, to fully achieve both accuracy and real-time performance, the system carefully schedules all modules based on the current condition. First, let's look at the ARIA's overall execution flow. The GPU runs full-frame inference. Meanwhile, the CPU manages dynamic region identification and camera motion estimation. In parallel, the NPU handles selective dynamic region updates and patch flow estimation. So to efficiently realize the overall execution flow we just discussed, ARIA introduces specialized scheduling strategies for the NPU and GPU. For the NPU scheduling, ARIA prioritizes dynamic regions based on their motion speed. Faster moving regions are processed first, ensuring critical updates are handled promptly. Slower or static regions are deprioritized or even skipped if resources are limited. Importantly, any skipped regions will have their priority increased, ensuring they are fairly processed in future inferences. Now, for the GPU scheduling, ARIA tackles the issue of full-frame predictions quickly becoming outdated due to abrupt camera motion or thermal throttling. During the offline phase, the system profiles the latency of full-frame inference across various resolution levels to enable fast runtime adjustments. At runtime, ARIA dynamically selects the optimal resolution based on current motion and thermal conditions, ensuring real-time performance without sacrificing too much accuracy. By coordinating resolution adaptation and priority-based scheduling, ARIA ensures real-time, high-quality inference even under dynamic runtime conditions. This slide shows the overall implementation of ARIA. We use TensorFlow Lite for DNN execution with GPU inference through the TF-Lite GPU delegate and NPU execution via the Qualcomm Neural Network delegate. Key modules like dynamic region identification, spatio-temporal alignment, and execution scheduling are carefully coordinated across CPU, GPU, and NPU threads. Lightweight MLPs in patch flow prediction are implemented with PyTorch. So now let's move on to the evaluation. So we evaluated ARIA on two devices, Galaxy S22 and Galaxy S24, powered by Snapdragon 8 Gen 1 and 8 Gen 3 respectively. For datasets, we used a custom collected dataset, pairing smartphone inputs with ground truth depth data from Z2 stereo depth camera. Our experiments targeted two tests, depth estimation and semantic segmentation. We compare ARIA against strong baselines including NPU only, MobiSys-alike, and ARIA base. We'll explain each of baselines right after. First, we show a qualitative comparison of VFM predictions across different baselines. NPU only runs full VFM inferences by low resolution, which suffers from low resolution artifacts. MobiSys originally divides the frame into several blocks and selectively does support resolution across CPU, GPU, and NPU. We slightly modified its approach to process each block across GPU and NPU, named MobiSys-alike, which introducing blocky artifacts due to frame splitting. ARIA base, a stripped-down version of ARIA without our solutions and just using block matching algorithm and simple 2D warping, suffers from inconsistencies between GPU and NPU outputs. In contrast, ARIA achieves clean, high-quality depth and segmentation results by combining full-frame fidelity with dynamic region updates. Second, we evaluate whether ARIA can consistently meet real-time latency requirements using deadline success rate as the metric. ARIA achieves a high deadline success rate of up to 99.9%, consistently meeting tight latency. On the latency graph, ARIA maintains stable end-to-end latency even under runtime variations. In contrast, MobiSys suffers from thermal throttling on the GPU, leading to high latency spikes and lower deadline success rate. Third, we evaluate how well ARIA maintains prediction accuracy. ARIA achieves up to 50% accuracy improvement in depth estimation and up to 72% improvement in semantic segmentation compared to the baselines. While NPU-only and MobiSys suffer from degraded accuracy due to low resolution and block artifacts, ARIA consistently delivers high-quality predictions across both tasks. Lastly, we evaluate system robustness under varying thermal and motion conditions. For the various motion conditions, ARIA maintains stable accuracy by dynamically adjusting its execution, while ARIA base struggles under the same conditions. For the thermal, ARIA reduces GPU temperature rise and avoids frequency drops by dynamically adjusting resolution based on runtime conditions. Compared to ARIA base, ARIA prevents sudden performance drops, maintaining stable GPU operation and end-to-end latency over time. This highlights ARIA's ability to stay robust under thermal stress. So, to summarize, in this work, we tackled the challenge of running vision foundation models on mobile devices, balancing high accuracy with real-time latency. We showed that single processor solutions fall short under these constraints. To address this, we proposed ARIA, a system that leverages parallel and selective execution across heterogeneous processors. Our evaluation demonstrated that ARIA achieves up to 99.9% deadline success rate and up to 72% higher accuracy compared to strong baselines. So that concludes my presentation on ARIA. Thank you for your attention, and I look forward to any questions. Thank you.
Thank you for the presentation. Please.
Okay, very interesting idea and great presentation.
Thank you.
This is Le Ming from Hong Kong PolyU. And my question is, so before I ask question, I need to confirm that. So you utilize CPU, GPU, and NPU to extract different information of a frame and merge them to complete the task. Is that right?
Yes, so it's correct. So GPU extracts the full frame, so full information on the frame, on that frame, and NPU just extract the partial information, which we set as the dynamic region, so which needs to be updated.
Okay, and so what information is extracted by CPU?
So CPU just handles the or module scheduling. So it just identify the dynamic region and carefully manage the threads between the GPU and NPU. So actually, CPU does not extract the information from the frame.
Okay, I see. And another question is that, so when processing a frame image, the CPU, GPU, and NPU are worked parallelly. So can I regard it as the latency is restricted to the processor that has the highest processing time? Let's say, so for example, CPU need 1 second to process, and GPU need 0.5 seconds to process, and the NPU needs less time. So the total time for processing a frame is 1 second. That is bounded by the CPU.
Yes, as you said in that scenario, but yeah, I'm not sure what you said about the CPU needs 1 second and.
Okay, maybe we can discuss later. Yeah, okay. Yeah. Thank you.
Hey, thank you for the presentation. Very
yes.
Nice. So my question is that I think some of your proposed techniques are still applicable for like the domain-specific model, right? Not the vision foundation model. I think those like dynamic region, detection, and that, device tracking, and temporal and alignment, right? The alignment module. Can you discuss like, okay, what if the user plug in this domain-specific model into your system? Would it still work? Can it support that kind of model? Perhaps on like more like lower tier device, right? You can imagine like eyeglasses, AR eyeglasses, right? With maybe only has GPU without any NPU, right? would it still, you know, like support this kind of device? Yeah, thanks.
So you mean this ARIA can be applied to other other hardware such as some low performance hardware? Is this your...
Like, can it work with the domain-specific model? That was my question.
So you mean my work can be also applied in domain-specific models? So I just said domain-specific models as the CNNs, but I think this work cannot be applied to CNN-based models because this work is totally based on the Vision Foundation model architecture, which I said as the patches. So CNNs does not have patch. So I think this work cannot be worked in the CNN-based model.
Because you have that encoder and decoder in your total architecture, right?
Yes.
Okay. Thanks. Yeah.
Yes. Thank you.
Thank you, Chanyoung.